Hi, and welcome to OzGrav's YouTube site. OzGrav is the ARC, Center of Excellence for Gravitational Wave Discovery. What that means is that we are a collaborative group of researchers across multiple universities in Australia, and we're all focused on researching the detection and the understanding of gravitational waves. Now, today, we are bringing you the first in a new series of talks. These talks are to showcase our amazing researchers and give them the opportunity to share the science that they love talking about. So today's speaker is Reinhold Wilcox. He is from Monash University here in Victoria in Australia. So Reinhold is a PhD candidate at Monash Astrophysics, so that's Monash University, and he is also a member of OzGrav's research collaborative. Reinhold really loves doing outreach and talking to the public, which is why we were really excited that he volunteered to be the first researcher to give one of these live stream talks. So he is a huge Star Wars fan, and when he's not doing his research and talking to the public about it, he also enjoys playing Battlefront 2. Now, we want to try to make this as collaborative as possible, so please post your questions in the YouTube comments or chat, and we will pass those on to Reinhold at the end of his talk. So now we will pass you over to Reinhold Wilcox and his talk, Waves in Astrophysics, Photons and Black Holes.
Thank you, Jackie. That was very kind of you. As she mentioned, my name is Reinhold Wilcox. I'm at Monash, and I'll be giving a talk today on waves in astrophysics, photons, and black holes. Now, this is meant to be a public talk, so if you're out there in the audience and I say something and it doesn't make sense to you, or if you have a further question, please be sure to enter into the chat. Looking forward to a lot of good questions at the end of this. But to start, I'll ask a very simple question. What are waves? And we deal with waves all the time in our day-to-day. Everyone's heard of sound waves and ocean waves. You may know of seismic waves that cause earthquakes. Of course, light is made of waves. Light is made of photons, but it travels as waves with, given frequency, given energy, all these different things that we can use to describe waves. And waves all have, there's a lot of differences between the different kinds of waves here. Sound waves travel through air and also water. Ocean waves need to be on the surface of ocean water. But there's a lot of things that waves have in common. And in order to figure that out, we need to figure out how to describe them. So to describe waves, there are many different ways, but the ones that I'm going to focus on here are looking at things like the frequency and wavelength and amplitude of a wave. So for those that don't remember from high school, a high frequency wave is one that has many different bounces back and forth over a short period of time. So you can see here on the top plot, the high frequency wave has many, many back and forths compared to the low frequency wave in the same amount of time. But a low frequency wave will have a longer wavelength. So frequency and wavelength are inverses of each other. The lower your frequency, the higher your wavelength. And then we can also describe the wave by its amplitude. And the amplitude is its height at its most deviated away from zero. Now, for the example of sound waves, the amplitude of a sound wave is interpreted as its loudness. So the louder you hear something, the higher that amplitude sound wave is. But the higher the frequency, the higher the pitch. So a very, very high frequency note would be heard as a very high pitch in a register. But we also want to emphasize that there's a range of detection, particularly for human detectability, that influences what we might interpret as sound waves. So, for example, the human range of hearing goes from about 20 hertz to 20 kilohertz, and this varies person to person, but that's sort of the typical range that you often hear of. But there are sounds way out of this range. So, for example, elephants will communicate at a frequency much, much lower than 20 hertz, but we just don't hear it. Similarly, a dog whistle is tuned to be outside of the range of human hearing, but within the range of dog hearing. So it'll be much higher than 20 kilohertz. But once we begin to study the full range of all frequencies of a given type of wave, we're studying the spectrum. And we can figure out what a spectrum is by splitting the light up using a prism. And I have this nice diagram here that shows white light being shot into a prism. White light is a mixture of all the different frequencies of light. But when it passes through a prism, the prism separates out those different frequencies. And what you end up with is this beautiful rainbow splitting of the different frequencies of light. As a matter of fact, the rainbow we see here is only a very small fraction of the full spectrum of light waves. And to see the full spectrum, it took us quite a bit of time to study it, but we can see it here. The full is enormous. I'm told my internet connection is unstable, so if there's anything that goes wrong, just let me know and I'll reset. But on the low end of the electromagnetic spectrum, so the spectrum for light waves, we have radio waves. Radio waves are the really, really long, really low energy waves that we use when we're communicating with radios, things like that. And we can actually go all the way down from these enormous radio waves all the way down to gamma rays, which are really, really high energy, short wavelength, high frequency waves. And again, I mentioned before that wavelength and frequency have this inverse relationship. So if you know your wavelength, you can take the speed of light, the known constant speed of light, and divide it by the wavelength to get a frequency. And that's how you can convert back and forth between these wavelengths here and these frequencies if you're curious. I'll mention that the only part of the spectrum that we can see is this small band here, the visible wavelengths, and that's why they have this rainbow in the bottom. Everything outside of that rainbow is stuff that we can't see with the naked eye. And for a long time, we didn't know that there was light that existed at those wavelengths. We thought all light was what existed in this prism. So this is pretty fantastic that we're able to access this whole spectrum now. And there's a lot of really interesting science that we can learn by doing this. But one of the important things to understand when it comes to these types of waves and spectra in general is the scale of the wave that we're dealing with. So a lot of times we'll talk about high frequency or long wavelength waves. But it's important to know that the scale of for example, a radio wave is anything larger than 10 centimeters. So if let's say you were to take a photon and measure its wavelength to be 20 centimeters, you could identify it as a photon from the radio frequency band. It would be a radio photon. And we can do the same for any of these other bands. This is a continuous spectrum. So whatever number you can think of for the size of your wavelength, you can identify it by its given frequency band. These differentiators, the 10 centimeters, 1 millimeter, are more or less arbitrary. These aren't strict boundaries, but it gives you a sense of roughly the scale and energies associated to a given frequency band. A lot of these might be familiar to you. You go to the doctor for an X-ray. You might have a microwave in your kitchen. Infrared wavelengths infrared goggles are often used to observe things that radiate heat. So anything that has a normal body temperature of about 300 Kelvin will radiate pretty strongly in infrared. And so as a result, something like a snake sees really well in infrared because it helps it to see prey that would otherwise be very well camouflaged. So a snake would have a different range of detection to a human as far as what it can see. But this is just to give you a sense of the size of these wavelengths. So you have infrared is down to the size of human cells. An X-ray wavelength would be about the size of an atom, all the way down to subatomic particles. So you can get really, really small, high energy photons. Small wavelength, high energy photons that we can still detect and do interesting science with. But this is, of course, to talk about astronomy and how we use the electromagnetic spectrum in astronomy. So you might be curious, if we were to look out on the sky in these different wavelength bands, what would we see? And I'll start here with the visible part of the spectrum. So in the visible part of the spectrum, this here in the corner is a picture of the night sky at visible wavelengths. So if you could look out, and this is pretty straightforward to do, if you could look out with a visible telescope or just your eyes, and if you had really good resolution in your eyes and you could take in a lot more photons than we can naturally, then you would see this. This is a long exposure picture of the night sky, but just in visible wavelengths. And at visible wavelengths, we can see things like stars, planetary nebulae, and supernova remnants. And here's a picture of a distant galaxy. So this is many, many stars. This is the Andromeda galaxy. There's many, many stars here that make up this beautiful picture. But if you had a powerful enough telescope with an eyepiece, you could look through and see this. This is only the case for the visible wavelengths because we don't have to convert from frequencies we can't see into frequencies we can see. We can see these. We just need a strong enough telescope to magnify it to a point where we're able to. This here is a supernova remnant. This is the Crab pulsar at visible wavelengths. I think this has been color graded a little bit, so it's not exactly true to what you would see through a telescope, but these are the wavelengths that you could see this at. So it would have roughly this shape. But we can also look in other wavelengths, such as the radio. And this is, again, the sky at radio wavelength. So these are the long wavelength, low energy waves. But because they're so long wavelength, it's very hard to capture them in dust or other things that might absorb other wavelengths of light. So a big issue with astronomy is that the wavelengths that show the things we're interested in might get absorbed before they get to us. So for example, it's very hard for X-rays to get through the atmosphere to Earth. So if you're looking out on the sky for X-ray sources, you can't really do it from Earth. You have to do it from space where the atmosphere can't absorb it. But radio is really cool because it's very hard for anything to absorb radio waves. So as a result, you can see really, really distant objects with some clarity. And some of the things that we can see at radio wavelengths are pulsars, quasars, and stellar nurseries. Now, let's start with stellar nurseries. This here is a beautiful picture of a stellar nursery. This is where stars are born. The stellar is star, and nursery is like you know a nursery here on Earth. It's a place where young things are born, and as they're growing into full-fledged stars. Stars are born from giant hot clouds of gas that condense into fusion machines. So this is what a star is. It's a ball of hydrogen and maybe some higher elements that just starts fusing. But in order to get there, you need to take a cloud of gas and collapse it. And this here is an example of one of those clouds in the process of collapsing. Of course, this might take many hundreds of thousands of years to actually collapse. So we'd only ever see this brief snapshot. We wouldn't actually see the collapse happening, but we're able to extrapolate from other things that we see and know to infer that this is a stellar nursery. Pulsars are also really cool radio sources. So a pulsar is a very, very dense type of what's called a dead star. It's called a dead star because it's the remnant after a star has died in a giant supernova explosion. I'll talk a little more about supernovas later. But if you have a big supernova explosion and you end up with a neutron star, you have this condensed ball of neutrons. And normally neutrons are found in atomic nuclei, where you might have maybe a couple dozen, maybe up to 100 or so neutrons and other things that look like neutrons, so protons packed into a nucleus with a huge amount of space around it. But in a neutron star, all that space has been taken away. So all of these neutrons are packed shoulder to shoulder, right next to each other in this very, very dense, compact ball. This object will be about the mass of the sun in an object the size of a city, to give you a sense of the extremely high densities we deal with. Because they're so dense, they have these very high magnetic fields, which generate magnetic field lines. And at the same time, they are also rapid rotators. And so what you end up with is these magnetic field lines that catch electrons and accelerate them off to high speeds along the magnetic poles. And that's what you're seeing here. That's these beams are accelerated electrons caught up in the magnetic fields. But you also have a spin axis. And if the spin axis is different to the magnetic field axis, then your beam will rotate around the spin axis. And you end up with this cool spinning top thing. Now, from far away, we don't actually see the neutron star. We can't resolve this shape. All we see is a flash of light whenever it points right at us. So we call these cosmic lighthouses. We can only see when it flashes right at us, which tells us the frequency of the rotation and the energy. And we can do a lot of really cool science with that. But these are mostly visible only at radio wavelengths. Similarly, we can look at background quasars. So quasars are the centers of galaxies that are very, very far away and radio loud. And because they are they're far, far away galaxies, they help us do a lot of measurement of movement nearby. So when stars move, because everything in space is so big, you don't see much movement. If you just looked out at a star and tried to measure it with, a ruler, you would never see it move. In a human lifetime, you'll never see with your naked eye a star move. But when we have really, really precise telescopes, we can compare, say, a pulsar in our galaxy to a background quasar. And because we know that the background quasar is so much farther away, it must be moving much, much, much less. So any movement relative to those two objects must come from the pulsar. The quasars make up, in a sense, a background grid from which we can use to measure distance, motion on the sky at radio wavelengths. We can also look at infrared sources. So as I mentioned before, infrared comes from, a lot of times on Earth, it comes from things that have a normal body temperature. And this is very helpful for a lot of things, but out in space, a lot of infrared is obscured by gas and dust. So as I mentioned with the radio waves don't get obscured very often. They can pass through things fairly easily without getting absorbed. But infrared wavelengths get absorbed quite easily into interstellar gas and dust. Historically, this has been a real problem because astronomers don't usually care about gas and dust. They want to see things behind the gas and dust that they might consider more interesting. And so for that reason, infrared wavelengths might not be particularly useful. But you can find uses for gas and dust. And in one particular interesting case, some colleagues of mine at Monash found that if you looked at gas and dust around early star systems, so very, very young newborn stars that are still surrounded by a cloud of debris, that cloud of debris will, over the course of many hundreds of thousands or millions of years, start to accumulate chunks, which will become small planets called planetesimals, and eventually grow into full-size planets. This is how planets are born, is in these disks around newborn stars. And what they found is that if you find a young star system with a disk around it, the disk should be a pretty smooth elliptical shape. So if you see any deviations from that, that's evidence of a protoplanet. So this is, I believe, the first ever exoplanet that was discovered using kinks in gas and dust disks around young stars. I just think that's really cool. We can also look at X-rays. So X-rays are really, really high energy sources. So this only happens when you have very energetic phenomena that happen to be pointing at us. You have to be very fortuitous. This is a picture of the night sky at X-rays, which I think is just the coolest thing. It's very beautiful. It almost looks like flight routes. But here's a picture of what's called an X-ray binary. So a lot of times what we see in space is that a lot of massive stars are in binary systems. And a binary system is two stars that are close enough that they're in orbit around each other. And depending on how close they are, they might interact. And one of the most common ways to interact is for one star to transfer mass onto another one. And this is what happens if they get too close. The gravity from one star will pull off material from its companion star. Now, in the case of an X-ray binary, the star that does the pulling is either a black hole or a neutron star. And black holes and neutron stars are your dead stars. These are the stars that are the remnants of supernovas. So a massive star blew up in a supernova, and the core left behind is either a black hole or a neutron star. And these objects are really, really, really dense. So if they accrete material, that material has to be squeezed into a very, very dense region. And the process is so energy intensive that it releases this beam of X-rays. So when we see X-rays like this, we can identify X-ray binary systems. And this is one of the best ways we have of finding black holes, because as you might know, black holes don't really emit light. So if you're out there looking for a black hole, you're not going to just see it. You need to find something that indicates that there's a black hole there. And X-rays are one of the ways that we use to do that. And then one of my favorite things to look at on the sky is the cosmic microwave background. So at microwave wavelengths, one of the most interesting sources is this background heat of the universe. So this is considered to be the farthest away thing that we can see in the entire cosmos. Way back at the Big Bang, Big Bang was 13.8 billion years ago. It was a huge amount of energy injected into the universe at once. It created all of this material, this hot plasma that over the course of the next 100,000 or so years, would cool into early hydrogen and a little bit of helium. And when this cooling happened, there was an imprint left on the sky of where these things were hottest, where the most matter was. And so this picture here shows you where there was matter clumping in the early days of the universe. And because it was imprinted in the early days, we need to look out really far to see it. So we need to look out to the far ends of the universe, as far as we can see, to see this background microwave radiation. This is about at 3 Kelvin, and I think it only deviates by about, I think it's 1/1,000,000th of a Kelvin. So these difference between the dark blue, the coldest regions, and the red, the hottest regions, is a very small fraction of the actual temperature of the background. So 3 Kelvin plus or minus 1/1,000,000th of a Kelvin gives you this beautiful picture of the early universe. And this is what tells us a lot about cosmology and how early galaxies formed, which informs how later galaxies formed, and elemental abundances and all this. It's interesting stuff. But you might ask, can we use the other waves that I mentioned earlier in astrophysics? We've discussed all the different ways that you can use light waves, but can you use sound waves, or can you use seismic waves to see things across the universe? And the answer is that to use any of these waves directly, you need a medium, and a medium is just a material. So for sound waves travel through air. They can also travel through water and other things, but typically we associate them as traveling through air. These are pressure waves. So as you speak, the air pressurizes and moves in some direction. Same with ocean waves and seismic waves. As soon as you take away that material, you take away its ability to propagate. So you cannot transmit sound through space. That's the end of it. For a really long time, we thought that light was the only wave that could travel without a medium. But then, at 9:50 a.m. on September 14th, 2015, we discovered gravitational waves. Here is a beautiful video of the gravitational waves produced by 2 black holes in a binary system. So as I mentioned before, these are 2 black holes that are so close, they're orbiting around each other. And because they're black holes, they have a lot of gravity in a small space. They're very, very compact. And when you have 2 compact objects in a close binary, it's a perfect recipe for gravitational waves. And you can see here, they're getting closer and closer. They're inspiraling. And right as they hit each other, you get a huge cascade of gravitational waves, and then it flattens out. And you have just a normal, much bigger black hole at the end of it. And this was a huge discovery. 2015, it was the first time that we found gravitational waves. It was a landmark discovery. And you might ask, where do gravitational waves come from? Well, there's a couple different sources. One of them is supernova explosions. So as I mentioned, you need a lot of energy to create gravitational waves. And supernova explosions are a source of a lot of energy. It's the violent deaths of massive stars. When you have a very large star that runs out of fuel, it will collapse on itself, and then the collapse ignites some things, and you get this enormous explosion. And it happens very quickly. The whole supernova might last about 20 seconds, give or take. But that means that your gravitational waves will be very, very high frequency relative to other things that create gravitational waves. And we can find these using laser detectors or laser interferometers. And here's a diagram of the laser interferometer. What you have is you inject a laser into a mirror that splits the beam into 2 different pieces, and then it sends them out on different paths and recombines them. And it uses the recombined light to look at the relative distances of the objects. And if you have the distances changing in a way that, if you have the distance to one light path changing in a way that's different to the other path, for example, if a gravitational wave were to pass through and shake the mirrors a little bit, then you could detect these gravitational waves. But more commonly, we find gravitational waves from merging compact binary. So this is the same as the simulation I showed just a minute ago, the video. But if you have 2 very compact objects, so black holes or neutron stars, in a close binary, they will radiate away gravitational waves. And because they're radiating away gravitational waves, they're losing energy. And when they lose energy, the orbit gets tighter and tighter. And this is a runaway effect until eventually they merge. So depending on the masses and the separations, you might find binaries that are very close to merging or in the process of merging, or you might find wider ones that will take a very, very long time to merge. But we can detect these using, again, laser detectors, either on the ground. So here's a picture of the Virgo inference detector in Italy. And here is a proposed, Here is a proposed space detector called LISA. This is the Laser Interferometer Space Antenna. And it's the same principle. So you have lasers traversing different routes, and you're looking for slight deviations in the length of the travel of these lasers. So if one becomes slightly longer because of a gravitational wave, they're very sensitive detectors that pick up on these changes and can say, yes, there was a gravitational wave that came from somewhere in that direction. These are mid-frequency gravitational waves. So these are going to be slightly longer wavelength, slightly lower frequency than the supernovas. We can also look at even lower frequency waves from supermassive black hole collisions. So this is the same idea as the black hole merger we saw a moment ago, but these are from supermassive black holes. Now, supermassive black holes are the size of 1 million suns. They have a mass of 1 million or more of our sun in one giant black hole. And they're so big, they live at the centers of galaxies. They're actually, there's some arguments that you need to have a supermassive black hole at the center of your galaxy to have a galaxy, to keep it all together. But they'll go on living most of their lives in the centers of these galaxies. But occasionally you have galaxy mergers. Now these take a really, really long time, many millions of years. But on the scale of the universe, these things will happen with some frequency. And when they do, you'll get that the galaxy and all of its stars will collide together and have this cool spray-off effect. But the supermassive black holes at the center will merge. And when they merge, they'll give off a huge amount of gravitational waves, but at a very, very low frequency because they're so much bigger, the in-spiral is a bit slower. And so in order to detect these, the frequency is so low that we can't use the laser interferometers that we showed in the previous slide. To do this, we need to use a network of high-precision space clocks. And to do this, we use pulsars. So I mentioned in the radio slide that pulsars are these spinning neutron stars, and we can see the beams of their radiation when they flash toward us. Now, pulsars are known to be extremely high precision, so we can predict when the next one will come with a fair degree of certainty. And if we have a network of these very, very precise clocks, then when we see deviations in their arrival time, so if we expect all the stars in this region of the sky to arrive at a certain time and they're all late, and at the same time, all the ones in this part of the sky arrive and they're all a little bit early, that's a giveaway that a gravitational wave passed through and it stretched space in the one direction and it squeezed space in the other direction. And as a result, we saw the signal from these stars sooner. We can only do this with these high precision clocks because we need that very, very high precision in order to do useful statistics. And then, of course, the biggest explosion that we know of was the Big Bang. So when the Big Bang happened, it was this huge dramatic explosion, and it also left a huge imprint on the universe in the form of gravitational waves. And it's believed that we can detect gravitational waves using the polarization of the cosmic microwave background that I showed earlier. So if we look at that background, we can find photons at all different, we can find photons of all different energies that tell us the temperature of the universe at that time. But if we also look at the polarization of those photons, that can be a giveaway that there were gravitational waves radiated away from the Big Bang. This would, of course, be ultra, ultra low frequency because they're so far away. They're not, the size of the universe. And that's why we need a universe-sized map in order to discern these polarization differences. If we put this all together, we can get a gravitational wave spectrum. And the gravitational wave spectrum is completely analogous to the electromagnetic spectrum. You have your very low frequencies and your very high frequencies. You have all these different sources that produce signals in a given frequency band. And you have all these different detectors that are designed to look in just that band. And there's a bit of overlap because you want to make sure you don't miss anything. But the point of this is just that with gravitational waves, we have a completely new spectrum with which to do science, something that we haven't had before, which is brand new. But it's important to ask how much of this spectrum have we investigated. With the other one, with the electromagnetic spectrum, we've done a lot of work across all the bands. There's still more to do, but we've detected signals in virtually every frequency band that we know of in that spectrum. With gravitational waves, that's not the case. The only place where we've discovered gravitational waves so far is here. It's very, very small section between about 1 and 100 hertz. And that's because that's the detectors that we built so far. This is a very, very new young field, and this is where we've discovered them so far. But there are plans to continue building larger telescopes, as the ones that I mentioned, the pulsar arrays and the cosmic microwave background and these space antennas, to allow for investigation into these other regions. So really, who knows what else could be out there, right? Everything that I showed are things that we know of, that we predict will show up in the gravitational wave spectrum at these different frequencies. But we don't know what we don't know. There could be something out there that we've not even thought about, and that's why it's so exciting to be part of this, because there's any number of mysteries to come. What does this mean for the future? Well, so Galileo first looked out onto the sky with a telescope in 1609. That's sort of considered the dawn of modern astronomy with a telescope, and that was 400 years ago. In that time, we discovered other wavelengths. We built up telescopes to see in these different wavelengths. We discovered all manner of crazy new stars and galaxies, and the origin of the elements, the size of the cosmos, how the Big Bang worked. I mean, these are really, really fundamental, cool questions that we've only in the last 400 years been able to answer. And then all the different frequency ranges that I mentioned before. With gravitational waves, we've only had 5 years. We're just beginning to scratch the surface. And already we're making huge discoveries in things like how binary stars work, and the formation of massive stars and old galaxies, and really, really cool fundamental physics. So there's a lot to be done, and we're excited to be doing it. But what does this mean for you? It means that for all of you that are here listening, that are curious about science and want to know more, ask questions. Ask lots of questions. Ask the tough questions. Those are the best ones, because if you ask a tough question, that's where you find out where the bounds of knowledge really are. Share your discoveries. Talk to your friends about this. Talk to your family. Make sure you share with them your enthusiasm, and stay curious. If there are any questions, I'll field those now.
All right. Well, thank you, Reinhold, for that talk. And we actually have had some questions come in. So we want to, I'll go ahead and pass a couple of those to you. So Beth had a question. She asked, is a protoplanet the same as a newborn planet?
Yes. Yeah, I'm not an expert in planets, so that's my sort of naive understanding, but the way I used it, a protoplanet is a planet on its way to becoming a newborn planet, sort of in the womb.
All right, that's great. Another question we have, so if you use a telescope for visible light and a radio telescope for radio waves, what do you use for infrared?
Same thing, infrared telescope. So we have X-ray telescopes, gamma ray telescopes, ultraviolet, and any wavelength you can think of, we have a telescope for that. A lot of them are up in the sky, up on satellites, because of the absorption in the atmosphere. But anything that we've made discoveries in, we have a telescope for that wavelength.
So we've got a telescope for that.
Yeah.
Great. And another question, which actually was from my son here, who was looking over my shoulder for a little bit. He asked, how far away are the pulsars?
You can think of, we have a telescope. Oh, it's a good question. So the whole galaxy is the farthest point of the galaxy from us is about 20 kiloparsecs away. And the galaxy is a disk, so we're on one side of the disk, and it's about 20 kiloparsecs to the far end.
Telescope for that.
All the pulsars that we know of are in that disk, so less than 20 kiloparsecs. But because we see closer things better, most pulsars are less than about 9 kiloparsecs away, and obviously even then most of them are within 5. So the whole galaxy
great.
Is,
and what I wanted to do was, this is, as the host, I get to ask one of my favorite questions. So you were showing that gravitational wave spectrum graphic earlier, and you pointed out that the only detection we made has been in a very small portion of that. So my question to you is, what future possible discovery are you most excited about? And what I wanted to do was, this is, as the host, I get to.
I think if so, one of the proposed ultra high frequency detectors is looking for spinning neutron stars with small deviations on it. So this is not a source that I mentioned, but similar to the supernova mechanism. If you have a pulsar that's spinning even with a
possible
very, very
discovery are
small
you most
mountain on
excited
it,
about?
that small mountain is enough of a deviation
What
to create very, very high
I wanted to
frequency
do
gravitational
was,
waves.
this is just,
And
as the host, I
this
get
would be
to
detected to
ask
detectors that are
one of
sensitive to a
the
higher frequency band.
questions.
But
You
if we were able
mentioned
to
that
detect them,
gravitational waves is
then it would mean we
there,
could discern
and you pointed
some
out
of the
that
really
it
cool
needs
fundamental
to
physics with
be
neutron
a
stars, such
very
as
small portion of that.
its mass
So
radius
a question
dependence.
for
So
you
an open
is,
question with neutron
do you
stars
think
is
you're
just
possibly
how big are they for a given mass? And it has a lot to do with really crazy nuclear physics and things like that, and GR that I don't understand. But there's a team of people with OzGrav, so you may be familiar with OzHF, that are trying to put together this ultra high frequency detector to look exactly for this.
Okay, great. So I think, we've gotten most of our questions asked and answered. And I did want to take this opportunity to say that if you want to learn more about gravitational waves, you can go on to OzGrav's YouTube channel, where all of you have found yourselves already, and take a look at the OzGrav documentary. It'll give you a little bit more information about what a big cross section of our researchers are doing. And also, next week on Tuesday, we will have our next in our online series of talks. We will have Isabel Romero Shaw, also from Monash University, and she will be talking about the origins of some of the words that are used in astronomy. So it should be a really interesting, a very interesting topic that I know I haven't heard much about. So I'm incredibly excited for that. All right, so I just want to thank you, Reinhold, for being here with us today, and thanks for your talk. And for those watching this in, you know, um, out there everywhere, please feel free to leave your comments. Go to YouTube's OzGrav to learn more, and hopefully we'll see you at our next talk. Thanks.
Thank you, Jackie.